point here, there's a couple of other things to consider, is you'll notice with this imine here, if these two groups were different, this carbon and this carbon, we actually would generate stereoisomers. So I think I have that next, and so we'll get to that one. Probably can do it right now, but why don't we cover it next? And so we have to think about, we could cover this, we could have generate different stereoisomers, but I wanted to actually, even though it's the last bit of the class, and this is kind of a big topic to cover, let's just reiterate what was seen in that video about this pH dependence, if it's okay with everyone. We'll go through this again. And what has been observed in this reaction, and I encourage you to take a look at that video again too. So I put it in there so we can see it, is that if you look at the rate of the reaction, you can see how fast the reaction occurs. So there's a rate constant, see some units like minutes, and you look at the pH of the reaction. What you would find is that the reaction rate increases as the pH is increased, and then eventually the reaction rate decreases. So for all of those that are fond of biochemistry, this bell-shaped profile looks like the pH rate profile for a number of enzymatic reactions, and so you'll see this in your biochem classes as well. And for those of us like me who work with enzymes, this has always been a good deal of our life. But this is an important aspect for a lot of reactions. And I think it's also important just to get out of the context a bit of writing all of these things on paper and seeing a little bit of how this works in the lab. So one thing to remember is the difference between a pKa and the pH when we're talking about something. Remember, the pKa refers to it's the acid dissociation constant of a particular group. And so there's a pKa for deprotonation of this iminium ion in the reactions or something like that. The pH is referring to the hydronium ion concentration in the solution, property of the solution. So what we find here is that as we're changing that pH, the reaction rate increases and decreases. So normally what this means is there's something that it's getting more and more favorable as you're increasing the pH, making the solution more basic. But then you get to a point where now making it more basic actually is unfavorable for something. And then I know this is just repeating what was in that video, but the key thing to think about is the first one makes a really nice demonstration, I think, is that our primary amine, this amine, could actually first be protonated. So this is a possible protonation state of that methylamine, and that would be in equilibrium with this species, the primary amine, plus H+. Okay? So then this primary amine to deprotonate has a pKa, so around 9 to 10. We're just going to round it up to 10. Okay? So then if you have a solution that has a pH of 10, then you have an equal concentration of the protonated form and the deprotonated form. So this goes back to Gen Chem. So if the pH equals the pKa, then it's a 50-50 mixture of the two. Equilibrium is just going back and forth. Protons coming on, going off, coming on, going off. If instead you have a pH of, let's say, 2, let's make this, this is 2, 5, 10. If you have a pH of 2, then you're pretty much entirely this protonated species here. So it's going to be 99.9, a whole bunch of 9% this particular species. If you're at a pH of, let's say, 15, you're going to be 5 logs above this. So you're going to have 100,000 times more of this species than this species. And I don't expect us to memorize the numbers. I'm just trying to give a perspective. So as we're going from a solution from a low to a high pH, what we're doing is we're going to increase the concentration from left to right. So a pH of 2 is mostly the equilibrium lies in this direction. Pretty much all of this is deprotonated. And then as we increase the pH, we deprotonate more of this and generate more of our primary amine. The reason for dragging us through all of this is that that's what we might actually observe in this reaction. Notice in this first step, we need to have the primary amine to act as a nucleophile and attack. This bottom species here, this is what's known as the ammonium ion. It's not a nucleophile. It doesn't have any lone pair of electrons. So that if 99.999% of your species here is the ammonium ion, very little is able to react. So you have a very slow reaction. Some of it is, this species, just a very small amount. It reacts. Le Chatelier's principle then moves a little bit more over here, it reacts. However, if you keep increasing the pH, then you end up shifting this equilibrium to have it favor more of the primary amine. One way to think about it is you're increasing the concentration of this species. So if you have more amine, you have more amine up here that's going to react. The reaction should happen faster. Okay? And so that's going to have an increase in the pH, leading to an increase in reaction rate. Now, eventually, you would get to a point where, let's say you have 99% of this primary amine around, and then if you go to 99.9% or 99.99%, you're going to see very small or incremental changes in the reaction rate. It would actually just keep going up, but you can't really detect it, so you would actually plateau someplace. So that can actually explain this increase. However, we also have this decrease in reactivity as a function of pH. That means we need to probably have something protonated for the reaction to occur. And actually, by going to higher pH, we're deprotonating something which is not good for the reactions. So it's actually slowing it down. And that actually occurs in this step over here, upper right, which I'm trying to highlight with the marker, is that in this case, we need to have a little bit of acid to turn this bad leaving group into a good leaving group. So it can be a protonated species. So if we keep on increasing the pH, sure, we're generating more of our amine, but eventually it will move on to also be decreasing the favorability of having our acid around and our protonated good leaving group. So that's going to slow the reaction down overall. So then what we would expect to see is a decrease in the reactivity as a function of pH. And that's indeed what you see in these reactions. The reaction rate goes up, and then the reaction rate goes down. So a bit of an aside, but this is something that you would actually observe in these reactions. This is this more complicated pH dependence. I'm bringing it up here to think about going back to the idea about pH and what that means, how that relates to pKa's, because I know in 220-A we talk a lot about pKa values, and then to see how that affects a reaction where you have multiple species. Some need to be deprotonated, some need to be protonated. And as mentioned at the outset here, for those interested in both organic chemistry and biochemistry, you'll see these sorts of features in a lot of different reactions. All right, so a lot to digest there. Let's just do one more thing here real quick. And so how about if we were to take this ketone and react it with this isopropyl amine and just a little bit of acid. We could draw the mechanism, just like what we had seen with the one above, that I made it so that we can no longer see it now. Let's just go ahead and draw the final amine product. So how about something that looks like this? Lone pair of electrons. However, that's only half of the story, because we would actually also see something that looks like this, the lone pair of electrons. And these two species are actually different, and so these are actually diastereomers of each other. Because just like with a carbon-carbon double bond, remember you could have diastereomers. So if we had a carbon-carbon double bond and we have something like this, about like this is going to be a diastereomer. Let's leave this side the same. Let's make this side different. Just as a refresher, if we wanted to actually identify what the conformation is between these two groups, we would go ahead and then conceptually just break this double bond in half, and then we would assign priorities. So now rather than R and S, we're using E and Z. So this is easy material, right? And so we look at priorities. On the left side, we have a hydrogen, and we have this isopropyl group. On this side, we have this ethyl group, 2 carbons, which is higher priority than that methyl group. And then we look and see in the double bond, of the 2 highest priority groups on the same side are different. Here they're on the opposite side, so this is going to be E. Although over here, this is 1, and what did I do here? Oh, sorry. Everyone's cringing, as you can see the mistake I made. I was wondering why they're going to do the same. I think I said it right, perhaps. This is 2. This is. I really want to write 1 on the bottom. I almost did it again. Okay. So here, the 2 highest priority groups are on the same side, or same side, as some people remember it. So zusammen. And then on this side here, 1, 2, and then 1, 2, opposite side are integrating. Yes, I got it right, James. So sorry, I'm going to end up on a bad note here. And then on this one here on the top, so we have, this is going to be 1 with our propyl, 2, this is 1, this is 2 with the lone pair, so they're on the opposite side, so this is E. And if I did it right, this is 1, this is 2, this is 1, 2, I think it's 5, and so this is zusammen. All right, gut genug. And so we still have the same E and Z nomenclature with these imines as well. So stereochemistry is there around every corner. You can use it as a quick refresher. If I did this right on the bottom, to go back to the E and the Z stereochemistry. So a lot of material today, going back to the carbohydrates in our discussion with all of that, the glycoside formation, but hopefully looking at the mechanism is very similar to what we've seen before. And then we got into the beginning here of thinking about imine and enamine chemistry. I'm going to scroll up for a minute here. And seeing we have this mystery yet, we've only covered half of it, that when we take these nitrogen nucleophiles, we can form the primary amine and imine with a secondary amine and enamine. We went through this mechanism of the imine, seeing that there are some subtle differences compared to what we've seen, but the overall process is essentially similar to the acetal in terms of a nucleophilic attack, proton transfers to make a good leaving group, forming this iminium ion on the bottom here, and then eventually the imine. We went into this slight complicated direction here, which I tried to cover a little more in that video about the pH dependencies, trying to bring some more of a reality to this. And then at the end, brought in this idea of stereochemistry, whereas I'll go back for a second, our acetone example here in the middle, this imine, I intentionally had both methyl groups be the same, so we didn't have to worry about stereochemistry. But if you can form diastereomers, you will. So then, what all do we still need to cover before Thursday's activity? I think 2 things. So we're going to mention just briefly some other primary amines. Nothing new in terms of chemistry, but just if you're interested in something like a hydroxylamine, and then we'll bring this into the context of what's known as a Wolff-Kishner reduction. I don't expect us to memorize this reaction, but I wanted to show it. So it brings home a point of what's known as a very good leaving group, actually. And then this secondary amine, since we've only covered half of the story, we're going to see the formation of an enamine. Everything is the same as what we've seen, except what's different. So there's just one subtle variation. I think that'll hopefully help make more sense. And then, so one more thing. So the additional amines, which will only take about 5 minutes. Wolff-Kishner to show what that is. Enamine to see the other side with the secondary amines. And then last, not to memorize anything, but just to put it into context, to review the reduction reaction, since we already were talking about those, we'll use this as a review of what is the reductive amination. And that one